Okay, thank you. I hope you can hear me all right. And as was said, I'm talking about building industrial applications, and I'm replacing my colleague Stefan Braun, who was originally supposed to hold it. So I've only slightly changed his slides, and I think that will hopefully go all right. So. The question that you have to answer often when you are offering Mathematica as a consultant in industries, is Mathematica fit for developing and deploying real-world applications in an industrial environment? And that has some implications that are probably known to some of you, but probably not to all. And I'm trying to just show you some of the implications that environment has. I want to first show you a few slides about Smartcie, the company that I work for, who we are, what we do, and why I think I have something to contribute about that topic. And then I will have a few words about Mathematica from the view of a developer, and I will also define what I think a developer is in that respect. And then I have an example where I show how an industrial application, in the sense that we understand it, is different from a usual Mathematica notebook and work that you're doing in science or in other areas. And then finally I have some conclusions, and I hope I can at least partially answer the question that is on the top of that slide. So Smartcie is a small company seated in Munich. We are 4 physicists and 1 engineer, and he brings us back to the roots sometimes. And we are using Mathematica as one of our main tools. It's not the only one. We are driven by our customers, so if they want us to use something else, we use something else. But if we have the choice, we often choose Mathematica. And I think for good reasons, and I try to explain why. Then we are specialized in building customized software solutions for engineering applications. And we have a long experience. My colleague Stefan, the founder of the company, is doing this for more than 20 years now. I myself do it for about 15 years, and we have done more than 250 projects in these years. So there is some experience, and we have seen quite a lot of the evolvement of Mathematica in the process. And yeah, so probably it's interesting to share some of our experiences. And well, it's probably also industrial applications can mean a lot of things. And for us, it's typically, because we're a small team and that's where we're good at, we provide inexpensive, easy to install solutions which are ordered and paid from the specialty departments. We're not so good at having big PowerPoint things to get an enterprise-wide big project, but we are pretty good at getting these small things done. And that's typically in the order of half a year, man-year projects, and we deliver a working solution which just helps them do their job. And I've been asked what Smartcie is, why we call ourselves like that. And I had to explain that we are not thinking that other people are doing dump CAE, but it's opposed to brute force calculations. And if you're in the engineering world, you basically have 2 kind of approaches. One is rule of thumb plus a factor 2 for safety. And maybe you have some Excel files that no one understands. And then on the other hand, you have 100 million finite element solutions which run on a big cluster and are sometimes crazy, and they are great, but sometimes they don't even give you the answers you want. So I think there is a gap in between those 2 extremes, and we're trying to fill that. Okay, that is something where I would say typical industries, the real message of this slide is there's no typical industry for us. We have been very different customers from different branches, and that's just what the top 6. But we have done other things, and even this list is not really giving you probably a pattern. It's similar to typical applications. We do all kind of engineering physics, applied physics. That's heat transfer, production processes, but it's also data analysis if our customer needs that. Sometimes these things are mixed. Actually, heat transfer is usually a mixed thing, because heat as its own is not really a problem and not very difficult to solve. But it usually comes not alone, but you have other effects, radiation, you have any kind of electro heat, and usually it's the combinations that's difficult, and it's also the combinations that is not always straightforward to solve with existing standard solutions. So I was mentioning that I'm trying to give you the picture of Mathematica from the point of view of a developer, of a professional developer of Mathematica-based applications in an industrial environment. That's a long sentence, and I try to explain what I mean with all these words. Professional means you have a limited budget, you have time constraints, and you always have to keep in mind that development, maintenance, support, all have a cost. So with Mathematica, you're usually very fast in developing, but you have to take care that that advantage is not eaten up by additional efforts for maintenance and support later on. So that's things that probably are different when you write your code for your own research work. Then it's great. You got your result, you publish your result, and the topic is finished. But if you deliver code to others, then you have to maintain, you have to fix bugs, and that makes it different. And then another big difference is that you work in a team usually, and that's something that is a big difference. If you write code and it's not your code, it's shared among the developers. And it's really a learning curve for everyone who starts working in an area, who comes from a university, that this is not your code, and it is good that it is not your code. Because if you are on holiday and the customer complains about a bug, you're quite happy that your colleague can fix it. It's a different thing, and people have to learn it, and it makes also, it has many consequences, like you're using a version control system. You can't go without one if you work in a team. That means notebooks are not really well suited for that, so you just switch to .m files. It's really little practical things that are influenced by such differences. A developer, I already said, is someone who writes code mainly for the others to use. It's not that you write code for you to use and then you share it. It's really, you're probably not even interested in running it once on your machine. You're writing it for someone else, and it is their ideas and their demands that you have to fulfill. It's also a big difference, and probably not everyday situation for typical Mathematica users, I think. And an application compared to a package is something that runs, and the user is not necessarily himself a Mathematica user, so he has no knowledge about it. He just he doesn't care in what language you have provided your application. He just wants it to work and to be easy to use. And then industrial is a wide field. I have just written some things here. You usually have to handle a full set of parameters. It's not enough to just concentrate on the parameters that are interesting in the problem, but you have to provide possibilities to give the full set. And you have to incorporate measured and real-world data, which often is large because people don't, they don't care if your application has problems, if that's 10,000 points in your interpolating function. They just have measured that and they want it to work. So you have to import it, you have to thin out if necessary, but you have to do that. They wouldn't expect a solution which just crashes. So that's something that often makes extra necessary to have some extra efforts. You always want units. These people are engineers, and there's good reason for having units everywhere. Then you have naming conventions that you have to respect, and there's also regulations and requirements that come from some corporate stuff, like you have to put your data in a certain form because they want it that way, and that's nothing that you will discuss with your customers. So, that is also, I think, a big difference. Then robustness is something that we are permanently addressing, because if someone pays you for writing code, he doesn't accept if it crashes. So, they will accept if it crashes once in a while, but the level of tolerance is very low. And that sometimes needs also extra efforts if you provide a Mathematica solution. And then you want something that is easy to use, interactive, with a graphical user interface, but you also want it to be possible to use that code in an automated way. So you can do parametric studies or optimizations, because this stuff is not run to learn something or to understand the model or something. They want to get answers, and so they can make decisions. So that's also kind of a difference. Now I have a few more general things about Mathematica. I think it is very well established in academia. It is also established partially also in industry for prototyping and for a first shoot, for new results, to try out a new method. That's where it is really well established. And in industry, you typically have Mathematica users all over the places, but they are the tool is more known as a personal tool for the rocket scientists, for those people who do the difficult stuff that no one else understands, and many don't understand why it's done at all. So it's in a corner where people often don't understand what people do, and I think that is not necessarily the case. It could be different, and I have a very simplified history from my own personal view. About the history and the evolution of Mathematica. It started to be known as a computer algebra system for doing symbolic stuff. And then it, from the beginning, had more capabilities in numerics than comparative programs. And it soon got really good in visualization, and that is the scientific platform that we all know and we all appreciate. And I think in recent years, Wolfram Research has tried to push it into a real all-purpose system, an all-purpose language. And to some extent, I think that is already in a good shape, but we are not completely there yet. And unfortunately, I also think that the use in industry is not as common as it probably could be. And well, I'm not in the position to tell you why. It's just a fact, and it's something that probably could be changed. So where does it shine? I think we have heard many very interesting and great talks about new features, and we all know where it shines. So I will have that short. I just want to emphasize that we use it for a reason, and we are very happy with it. Especially, and I just couldn't resist to add that to those slides, is from an engineering point of view, the numerical differential equation solvers are really great. I mean, they are really good and comparative with everything else that you can have in the market. And there were new things in version 9, like parametric and dissolve and when events, and now in 10 there's finite element methods. And to some extent, I sometimes feel that even Wolfram research themselves underestimate the power that dissolve has. So thank you for having that, and I hope especially the finite element method will make more progress, so it really fulfills all that what you can expect from it. So we also have recently, within the last year, seen a wide variety of possibilities to deploy your applications. We have always had Web Mathematica, I mean, at least 10 years or so. We have had Wolfram Player Pro, which is quite interesting part if you try to sell your Mathematica code, because it is a relatively inexpensive runtime environment, so you can just give your customer that thing plus your code, and it will run like a complete Mathematica for only a fraction of the costs. There's CDF, which is in a commercial environment. Usually, at least in engineering applications, it's missing the possibility to reach data. I mean, that is something that you usually need. But it's good that it's there, and then there's now cloud and Mathematica Online. I think there will be some other interesting ways to deploy your applications. Unfortunately, there are also some dark corners, and that's a bit of a paradox situation for me, because usually I need to convince my customers that it makes sense to use Mathematica as a platform for developing serious applications. Now, today I'm a bit in the different corner, and I'm just pointing to some things that if you ever think about using it for that purpose, that I think you should be aware of. And probably it will also be changed in future versions. One thing that I'm missing is an ecosystem. That is, when you look at other languages, you typically see how they advertise their ecosystem, like libraries that you can, automatic installation of libraries and all these things, like comprehensive Perl archive made Perl attractive. Not so much the language, but just this feature. And we're missing something like that, I think, in Mathematica. But there is also an ecosystem, and demonstrations is something that is, I think, very valid. If you just search something to see how can I approach a problem that is new to me, then you certainly will find something there. And Mathematica Stack Exchange is also something where you can get high quality answers from all over the world. So there is some good things, but I think it could be better. Another thing I'm missing is the attraction of developers. So usually, and I would be interested to see if there's an exception, people come from Mathematica and then they turn to a developer. It's hardly ever that you find someone who is a developer and chooses Mathematica as its language, because it just doesn't happen. And yeah, it's just a fact. And well, that is something that I think you would have to work on if you really want to establish Mathematica as a platform for application development in a professional environment. If you try to search a job posting where a Mathematica developer is searched, you probably will not find one worldwide. So I think that's really something that would be nice to see to change. Yeah, certainly. Yeah, you and me. And honestly, some parts of the code are not robust enough or hardly robust enough to really qualify as industrial strength. So degree functionality, if you do something complex, is really hard to get fluid and robust. If you need to get your stuff to disk and load it, import, export, that all is there and it works. But if you have big data, if you want it to be fast, then you often find corners where you have to do your own thing. Now, another thing is the Wolfram Workbench. I don't know, is version 3 out? I don't know. I'm waiting, I think, for 8 years that they update this, and that would be a useful tool if you're a developer, and it's just, well, not on the top of the priority list. Then there's no useful debugger, which is something you're really missing if you come from another language. Now, people who use other languages always ask me, how can you live with a debugger? And when I do projects with other languages, I really miss a debugger for about a week. I mean, I've learned to get along without one, and I think we all have learned to get along without, but this is something that is missing, and especially if you write complicated dynamic code, a debugger would make your life easy. That's also something, from a developer point of view, you would wish to have more control over the dynamic language. I mean, it's really impressive that you just have a one-liner and you have an interface. That's great, and I don't want to change that. That gives access to these functionalities to people who would never learn an event-based library for whatever. But if you work as a developer, you just need more control, and if something doesn't work, you want it to work and not to just find a workaround. So that is something that is high on my wishes. There are some other things, but I think I leave it at that. The good thing is that you can do it yourself. So there is JLink, there's Netlink, there's LibraryLink. So you have all possibilities to code that stuff that you're missing, and then you get your stuff done. So although there are some parts that are not good enough, probably you always can replace it with something that is hopefully good enough. But it takes efforts, and well, it is a kind of annoyance if there is import for an HDF5 format, and if I try it, it can't do what I need, so I have to program it myself. So that it's sometimes also a surprise which makes you miss your budget. So I have here just an example, and that's heat transfer, which is something that we often. The rollout?
The last one, deploying player pro application system server packages. What's the problem?
It's not a problem, but it's inconvenient. If you have an application with 30, which consists of 30 .env files, some notebooks or palette files, and you have to pack all that, and you have to encode it so it runs and you want to pack it to something, and I'll probably show you what we have programmed ourselves. Our customers are not IT personnel, so they want one button to press and install it, and that's something that is, you can do it all in Mathematica, but it's not there. So, okay. Now this is from the demonstration page. I'm not really trying to show you anything interesting here. It's just to show the difference. I mean, this is a really great thing. So you can learn a lot and play with the parameters, but it's kind of limited because some parameters are missing, or you have another one. That one over there, that's the nonlinear case when the material is temperature dependent, the material properties, and you won't find something that would let an engineer do a layout for insulation of an industrial oven or something, because you would need all the features that these demonstrations combine in one application. And also, that's typical things. You have here fixed 5 or 6 layers. If someone needs 7, he can't do it with that. So you have to just provide something so you can change the number of layers. And now this, I don't know, can you see it? This is the same problem in one of our applications, which is one of the very simple ones. But you see that it's not interactive now, but you can just add rows here to add layers, and you can just choose from a material. You can define your own materials. You can read the material properties from an Excel file from measurements. So you have temperature-dependent material data and all these kinds of things. And yeah, then the real plot looks not much different, but engineers usually want a number. It's probably not easy to see, but there's a number and a unit, so they know there is, in that case, that the radiation heat coming in, and that is by convection, there's some amount of heat coming in, and there's something going out, and they can't just, and this is a sum, and they just can read off numbers. And that's also something that the plot is always nice to see, and it gives you the impression that what is calculated is okay, but it's not the full thing. And typical thing is you don't have a single wall, but you have a box with some material inside, and then that's 6 walls. So you need something that scales. You have now 1 wall, now you have 6 walls. There's also 4 cool packages, and the whole thing is a temperature, cooling packaging, which is sent around. And so at a certain point, you're more involved in managing your parameters than actually solving. And NDSolve is great, and we just push it to NDSolve in the end. There's some code that uses finite volume methods to generate an array of differential equations. But the real challenge is to handle all these parameters in a useful way. Now, you choose that example is something that we are selling as a product, and you can choose a temperature profile. And again, you just have a tabular data. I mean, engineers, just like the business people that we have heard in the morning, love tabular data, and you have to just provide something that looks a bit like Excel, so they get warm with it. And then you would choose some more technical things, but you don't have to. There's a decent automated parameters. I just want to show you that even this relatively simple package ends up with an amount of 2,500 equations, and then you solve it in about a minute or so, and you get the temperatures at various points in that thing, and then the engineer can see whether the product that he wants to send with that package is within the admissible temperature range or not. And well, that's something that is nice to sell such a product, but it's not of much use to the end user. It just shows that it's really a 3D calculation of the temperatures within that thing. And then another application here is in combination with that temperature package. We're using weather data to get statistics of what would you expect 1st of June to be, what temperature range would you expect from the 1st of June? So we use weather data, historic data, make some analysis, and then we can give you the 95th percentile of certainty that the temperature won't be more than 30 degrees. And from that, you can automatically build a temperature profile, which you can then calculate with the other package, and then see what happens and if your product is still alive. So that's basically what I wanted to tell you. Now the conclusion is, can you use Mathematica for application development? And I would say yes, you can, but you need to bring some enthusiasm and quite specific knowledge to succeed. So it's not something that's just with a finger tip. And the more interesting question is it a good choice? And that's more difficult to answer. And I would say if your topic and your task can make good use of Mathematica's strength, then yes, it can be a good choice. But there's again some small print. You should ensure that all participants are convinced that this is a good solution, because unfortunately, Mathematica is very easy it's very easy to make Mathematica look bad. If someone wants, he just does something stupid, we all know it's stupid, but it just ends up in Mathematica crashing and people say it's not good. So you really need to be sure that everyone agrees on that decision. And then I think you can do very successful projects. And you should always expect when you try to do something like that, that you have to code some stuff yourself. It's not a big problem. You're a developer, you should be able to do that. But you have to do some things yourself that are kind of off topic for the stuff you're doing. Like I wouldn't have expected me to write a packaging mechanism and an installer, but that's some stuff you usually end up with. So thank you.